Okay, Chris, Ivy, David, are you guys ready to go?
Yep.
We're ready.
Yep.
Okay, well, thanks and welcome everybody to the second of our occasional ECS and Cloud Feedback virtual symposiums. My name is Andy Dessler, and we have three really good talks for y'all today. Let's go over a few seminar notes. So we have three AGU style talks, and the order we'll go in is Chris, Ivy, and David. So the talks are 12 to 15 minutes. So we have plenty of time for questions. If you have questions, you're welcome to type them into the chat box at any time. Or if we know that some people don't like to ask or type long questions. So if you want to ask your question via voice, just raise your hand. If you go into the participants list, there's a button for raise hand, and we will unmute you and you can ask the question. And then at the end, what we did last time is we had a few minutes for general questions and answers, discussions. The speakers will hopefully be able to stick around and answer kind of general questions after the last talk. We'll see how that goes. All right, so that's all I have to say. So I'll turn it over to my co-organizer, Christy Prosescu, who will start running the show. Christy?
Hi, everyone. Well, I think my only job now is to tell Chris to share his screen and take it away.
Okay, thanks very much, Andy and Christy. So can you hear me?
Yeah, it looks good. Just go into full screen mode. Yeah, perfect.
Excellent. Yep. Good. Okay, so thanks to Andy and Christy for giving me the opportunity to talk to you today. So hopefully this is not going to be too much of a diversion from the sort of core focus of this community, really. But I'd like to talk about the sort of interactions between aerosol forcing and climate sensitivity, and particularly the time history of aerosol forcing. So what we're looking to do is to come up with this time history of aerosol forcing that satisfies observational constraints of temperature and energy, Earth's energy uptake. And we're going to do this using CMIP6 models so far as possible, and then constraining those outputs to correct for model behavior based on energy budget constraints. And then right at the end, we can actually use this procedure to attempt to constrain climate sensitivity. So hopefully there's a bit of interest for this particular community. So there's been a kind of a last 20 years or so research on the interaction between radiative forcing and particularly aerosol forcing and climate sensitivity. And in CMIP3 models, there was a strong negative correlation between aerosol forcing and climate sensitivity. So here we have the total forcing on the y-axis, but almost all of this model spread in CMIP3 is due to the aerosol forcing. And then when we move forward to CMIP5, this correlation kind of goes away. But then when you actually just consider the models that include an aerosol indirect effect, that negative correlation between climate sensitivity and aerosol forcing returns. So these points in red here. And then in CMIP6, we actually find that there's no correlation at all between the present day aerosol forcing and climate sensitivity. So what that does kind of indicate is as CMIPs have progressed, that the observational constraints, particularly of temperature, have been used less and less as a way of tuning models. So we can't really obtain any estimates of climate sensitivity just based on the present day aerosol forcing in climate models. But what we can do is we can use an energy balance framework with a large ensemble, and we can take lots of different samples of radiative forcing and climate sensitivity and run them through energy balance models. And then we end up with this distribution that is sort of quite quite negatively correlated between climate sensitivity and aerosol forcing. And I certainly wasn't the first to do this. So Chris Forrest did this in the early 2000s, and there's been several others on this particular study. But what I'm interested in here really is less to do with the present day forcing and more to do with that time history, particularly in the second half of the 20th century. So we compare here 7 models from the radiative forcing model into comparison project. So on this left figure here, the coloured curves show you that effective radiative forcing from 7 models, and this is just the aerosol component of the forcing. And we're trying to link to this suggestion that the aerosol forcing over a lot of the 20th century is stronger in CMIP6 models than has actually occurred in reality. So there's a paper recently accepted from Flynn and Morrison, it's an ACP, showing the, on the right here, showing the correspondence between CMIP6 model temperature in red and observations in black. And as you can see, the CMIP6 models are quite a bit cooler than the CMIP5 models in blue. So it's been hypothesized in that paper and by others that there was a pretty strong aerosol cooling over the 20th century. And then as we get towards the end of the 20th century and into the 21st, we see that actually the CMIP6 temperatures catch up with the observations and actually sort of are about the same as the observations as we get towards the present. So that indicates that there's a sort of a more recent era of greenhouse gas dominated warming that's in correspondence with high transient and equilibrium sensitivity in CMIP6 models. So what we've done here is to use the 7 CMIP6 models we have available with the transient forcing and fit simple emissions-based forcing curves. So what we've done is we've separated the aerosol forcing from 1850 to 2100. So it's run under SSP2 4.5. We've separated it into the direct and the indirect forcing. So in sort of in AR5 onwards parlance, that's the ERF ARI and the ERF ACI. This was done using the approximate partial radiative perturbation method, which is it's a fairly good method to get this split. And we fit these simple emissions-based curves to the forcing in each model. So we have the direct forcing is linear in emissions of SO2, black carbon, organic carbon, and the indirect forcing is a logarithmic relationship based on emissions of SO2 and BC and OC. So that second relationship is rather simplified given how complex processes in cloud formation and aerosol indirect effects actually are in reality. It's an extension of the Bjorn-Stevens relationship for SO2, and we've added the additional term for BC and OC based on it's a very good fit actually to a more sophisticated offline aerosol indirect model that Steve Garn and colleagues came up with. And as you can see from these correspondence to CMIP6 models in the figures on the right, these simple curves, when you use the right parameters, give a very good fit to the aerosol forcing coming out of the models. So what we do is then we take, based on those 7 RF MIP models, we sample those 5 parameters that govern the aerosol forcing, and we take a 25,000 member ensemble with those parameters informed by the CMIP6 models. And we generate 25,000 different time histories of aerosol forcing. And we correspond these shapes that come out of that Monte Carlo ensemble to the distributions of direct and indirect forcing from the recent Ringberg assessment from Bello et al. So this was a paper that took various lines of evidence into account to come up with the most likely distributions of 2010 and versus 1850 aerosol forcing. So we use 2010 and 1850 as the anchor points, and we shift back to a 1750 baseline because we're looking for a sort of a real pre-industrial year to evaluate our aerosol forcing against. And then we generate these 25,000 different aerosol forcing time series. And on top of that, we also take the same Monte Carlo style approach for other components such as greenhouse gases, and volcanic forcing and ozone forcing. Although these are generally a little bit less uncertain, especially in the shape of their forcing over the history. So they're not the main focus of this study. We take also a few different alternatives as well. So as well as this emissions-driven SSP run, we also look at an alternative data set from Eclipse. And we also use the 7 models specific forcing shapes as well, just scaling the magnitude of the forcing. And one further data set we use on top of the 7 CMIP6 models is from the Oslo CTM3 model. They also produced a 1750 to 2020 aerosol forcing assessment using that model as well from the Lund et al. Papers. So with the aerosol forcing time series, we combine that with the 2-layer climate model. So this is rather than trying to run 25,000 ensemble members in a GCM, which is never going to happen, we take sort of a very simple representation, sort of physically consistent 2-layer climate model. And we also tune these based on CMIP6 models. So we have 44 CMIP6 models that give us parameters for things such as the climate feedback and the heat capacity of the 2 ocean layers and how that heat is exchanged between the 2 layers. So we also take 25,000 samples of these distributions, which take into account the correlations as well between the different parameters. And we run that through that 2-layer climate model, which gives us the temperature, and it also gives us the ocean heat uptake. And we also add on internal variability. So that's statistically generated internal variability based on 49 CMIP6 pre-industrial control runs. So we constrain these temperature and ocean heat uptake simulations from the energy balance model to observations. So for temperature, we look at the 1850 to 2019 period from Coughton and Way, and we apply a small correction to that as well to try and estimate what the global near surface air temperature would be given the blended global mean surface air temperature from Coughton and Way. And we match how well our 25,000 ensemble members match the observations using a simple root mean error score. And to ocean heat uptake, we look at recent data sets that attempted to estimate all of the heat uptake in the Earth system from 1971 to 2018, and we look at that using a linear trend, as there's a lot less interannual variability in ocean heat uptake than there is in temperature. And then we give each of the 25,000 ensemble members a score based on how well they meet those 2 constraints. So we have, towards the left of this log-log histogram here, we have ensemble members that don't match the observations very well, and they get a very low weighting, whereas there are a few ensemble members that do match both constraints very well, and they get individually quite a high rating. So when we put all this together, we obtain a time history of aerosol forcing. So I've taken the direct and the indirect components, and also the total aerosol forcing, and we get a best estimate from 1750 to 2010 of about minus 1.1 watts per meter squared, which over the last few years has recovered to about minus 0.9. The reason for this being that in recent years aerosol emissions have decreased, particularly SO2, And actually, the underlying SSP data sets, there was a large decrease in SO2 going from 2014 to 2015. If you compare this thin, thick grey curve with some of the colour curves, some of the CMIP6 models, and these are the scaled ensemble members as well, then we find that some of the CMIP6 models are showing an aerosol peak cooling that comes too soon, followed by a rapid recovery. And this could be driving some of the rapid warming that is seen in the historical, towards the end of the historical period in some of the CMIP6 models. So when we try and we can actually look at taking the two-layer model parameters and to constrain climate sensitivity. And the first thing to kind of notice here is that we actually constrain out strong values of aerosol forcing and also high values of climate sensitivity and transient climate response. And we come up with distributions of ECS that are, with a best estimate of 3, with a range of about 2 to 6. Now, admittedly, that's not very tightly constrained, but our best estimate is quite a bit lower than the CMIP6 model mean, which is about 3.7. So I'm just going to come to the end of this presentation here. So coming back to the first question, is the 20th century CMIP6 aerosol forcing too strong? It's quite difficult to tell from a sample size as small as this, but maybe it is. So from the 7 models we have, these are the smooth aerosol forcing here. We see that 4 of them are sort of generally below the best estimate, and 2 of them recover quite quickly. So we can't really say anything conclusive about CMIP6 as a whole based on these 7 models, but there is kind of some suggestion that some of the models that are out there do have too strong an aerosol forcing over the 20th century. Okay, so just to conclude quickly, so we use the simple emissions forcing relationship in an engineer balance model tuned to CMIP6, trying to use observational constraints to correct for the time series of aerosol forcing that's coming out of CMIP6 models. And we can then apply these constraints to come up with a range of present-day aerosol forcing, ECS and TCR. And there's some evidence that CMIP6 aerosol forcing is too strong in the 20th century, but we probably need more models to participate in the radiated forcing model into comparison project for that to be more conclusive. So thanks very much for your attention, and I look forward to taking questions at the end.
Great talk, Chris. Thank you so much. So people can just type their questions into the chat and I'll read them out loud, or if you want to ask them, just use the raise your hand function in the chat. So we have one question now from Karsten. Hi, Chris. What is the reason why CAN ESM5 and GFDL4 have this early negative ERF, early peak negative ERF?
I'm not sure. So there's a couple of things to say. The first one is that we have sort of used that approximate partial radiative perturbation method to fit the emissions time series to the forcing, and there can be a small residual in that effect. But actually, if I go back to I think this slide here, not this one here. So this is actually the smooth. This is smooth, but this is the native model forcing. So there's no scaling applied to this. So we do see, especially with GFDL, that there is quite a recovery. So this is SSP2 4.5 up to 2025, going from 1975. So that would purely be what the models have derived based on the emissions they're given. But this diversity in model forcing is something that we should actually be celebrating, because it gives us a lot of different histories to go on, and lots of different ways we can explore this parameter space for the historical forcing.
Cool. I think we have time for one more question. Nader, you should be able to unmute yourself and ask your question.
All right. Thanks for the talk. Zooming out a little bit. So when we just have the surface temperature record, then we've got one constraint and two unknowns where the aerosol forcing and the climate sensitivity are unknown. Seems one significant thing you're doing here is adding a second constraint, which is the heat uptake or the TOA imbalance. And then you're able to constrain both things, climate sensitivity and aerosol forcing. Are there other studies that have done this? Is this study original in that respect? If other studies have done this, how do your results compare?
Yeah, that's a good question. So yeah, so it does actually go back to the sort of Chris Forrest papers, sort of in the early 2000s, where they definitely did use it's either ocean heat uptake or ocean sort of diffusivity as a constraint. I think where we're coming in slightly different here is actually using this to constrain a whole time series rather than a sort of a particular. Okay, we are doing the pre-industrial to present day, but I think we're also looking at how some of these CMIP6 models are evolving over time and how they are projecting their GMST projections and how that corresponds to the observations, and trying to basically correct for that based on these observational constraints. I think that's kind of where this work is kind of a bit novel and hasn't necessarily been done before.
Great, thank you.
Okay, there's a lot of interesting questions, and hopefully we'll have some time at the end and people will stick around for a Q&A, but right now we need to move on. So our next speaker is Ivy Tan, who is starting as an assistant professor at McGill, and she's going to be talking to us from her transition there about extratropical cloud feedbacks.
Yes, so just let me get set up here. Okay, so thanks for the invitation to speak in this seminar series. In the next 12 or so minutes, I'll be talking about, I'll be talking about all things extratropical cloud feedback. So it's uncertain sign, contributing processes, and potential observational constraints. While this feedback may seem like just one part of the puzzle, it appears to be an important part for understanding the higher climate sensitivity in the CMIP6 models. Before I start, I'd like to acknowledge my collaborators who have contributed to this work: Trudy Starelmo, Lazarus Oriopoulos, Donovan Barahona, Mark Zelinka, Brian Kahn, and Dan McCoy. So here's the outline of my talk. As the title suggests, there are three parts to it. The first part provides the background and context for the extratropical cloud optical depth feedback and its role in climate sensitivity. In the second part, I'll go over some of the processes hypothesized to be important contributors to the feedback. And then finally, in the third part, I'll talk about potential observational constraints based on some current work in progress. So without further ado, let's start with the first item: why the sign of the cloud optical depth feedback in the extratropics is uncertain. In CMIP3 and CMIP5 as well, the ensemble net cloud feedback at the top of the atmosphere is negative in the extratropics, as shown here in the far right panel. In other words, extratropical clouds respond to global warming by cooling the top of the atmosphere. This total feedback can be broken down into these three components on the left-hand side: cloud opacity, height, and cloud fraction. And what I want to draw your attention to is the fact that the cloud optical depth feedback on your far left here, which I'm going to denote by lambda sub tau, is the primary reason why the total cloud feedback in the extratropics is negative. And this is a reflection of the fact that extratropical clouds become more opaque with global warming, which makes them more reflective to sunlight. Now, at the top of the atmosphere, the impact of the change in cloud opacity on long-wave radiation is relatively weak. So the overall effect is a net cooling, making the feedback negative. And so now a natural question to ask is why extratropical clouds become optically thicker with global warming. And one physical mechanism for why the extratropical cloud optical depth feedback is negative relates to thermodynamic phase shifts in mixed phase clouds that contain mixtures of both supercooled liquid and ice. In this mechanism, called the cloud phase feedback, a warmer and deeper troposphere causes cloud ice in the initial climate state to be replaced by cloud liquid. But liquid droplets tend to be much smaller in size and also just less abundant than ice crystals in general, making the clouds more opaque to sunlight, which counteracts the initial warming, making this a negative feedback. A convenient metric to quantify the amount of liquid versus ice in the initial state of the mixed phase cloud is the supercooled liquid fraction, or the SLF for short, which I'll be referring to throughout my talk. It's simply the ratio of the amount of liquid to the total amount of liquid and ice in the cloud. Alternatively, another metric is the T50/50, which is just simply the temperature at which half the clouds are glaciated. So now, a long-standing bias in many climate models is that they underestimate SLF compared to the observations. And as we just discussed in the previous slide, this makes the shortwave cloud optical depth feedback more negative. The CESM model was a typical model with this low liquid bias, and when we removed the bias, we found that the model's climate sensitivity increased, primarily due to a less negative cloud optical depth feedback. However, a closer look at the geographical distribution of the feedback shows that the feedback is not only less negative in the extratropics, as SLF increases here going from left to right, but it actually unexpectedly turns positive, which the cloud-based feedback cannot explain. So what this means is that correcting for the low SLF bias weakens the negative cloud phase feedback to the extent that it actually starts to unmask an underlying positive cloud optical depth feedback. Using zonal averages to illustrate this with our CESM model here on the left panel, you can see how dramatically less negative the feedback becomes going here from the solid line to the dashed dotted lines here where the simulations have higher SLFs. And when comparing this side by side with the change going from CMIP 5 shown in the blue curve to CMIP 6 going shown in the orange curve here, the same pattern is being mimicked in the latest CMIP models, as Mark Zelinka had discussed in the first seminar series. In addition to these studies, Turai et al. Had also independently suggested the possibility of a positive extratropical cloud optical depth feedback using passive satellite observations. So the take-home message for the first part of my talk is that there's evidence suggesting that the extratropical cloud optical depth feedback might actually be positive, contrary to the CMIP 3 and CMIP 5 model ensembles, making the sign of the feedback uncertain. So that's how cloud phase impacts climate sensitivity, but I just wanted to mention here as a brief aside that very different behavior occurs locally in the Arctic. Here, downwelling long-wave radiation from low-lying liquid clouds plays an important role at the surface. In fact, so much to the extent that the low SLF the low ECS simulations turn out to have greater Arctic amplification. And that's all I have time to say for now in the interest of time, but you can refer to our paper for more details. Now, an important step in reducing uncertainty and better constraining the cloud optical depth feedback is to determine the underlying processes involved and their relative importance. So this now takes me to the second part of the talk. Here I'm showing our attempt to break down the extratropical cloud optical depth feedback using MODIS satellite observations. To be more exact, we're actually breaking down a proxy for it, but without getting into the nitty-gritty details, ultimately our method gives us contributions to the cloud optical depth feedback owing to liquid clouds that's shown by the blue here, ice clouds that's shown in red, and the thermodynamic phase shifts in between them, which is shown here by the green curve. And I want to highlight two features from these plots. The first is that the green curve is always positive, which is a reflection of the fact that shifts from ice to liquid clouds always increases cloud optical depth, which is consistent with the cloud phase feedback. Now, the second feature I want to point out is that the blue curve is always negative over the mid-latitude oceans. And relating this back to the climate models we saw in the first part of the talk, this plot basically tells us, using satellite observations, that liquid cloud processes are causing the cloud optical depth feedback to be positive. But specifically, what are these liquid cloud processes? One hypothesis we're currently exploring is that shifts from optically thicker stratocumulus clouds to optically thinner cumulus clouds contribute to a positive cloud optical depth feedback in the extratropics. These stratocumulus to cumulus shifts I'm referring to are analogous to those occurring on shorter time scales in the subtropics. And we're testing this hypothesis using cloud type classifications based on MODIS cloud regimes. Using these cloud regimes, we've broken down changes in the natural log of cloud optical depth in a 14-year period into changes that occur both within the cloud regimes and those occurring between the cloud regimes according to this equation here. And over the Southern Ocean, where the surface temperature has been cooling over the recent 14-year period that we're looking at, what we're finding is that the stratocumulus clouds are increasing in their frequency of occurrence, while the cumulus clouds are decreasing in occurrence. So overall, this is causing cloud optical depth to increase, which is consistent with an overall positive cloud optical depth feedback that these shifts from stratocumulus to cumulus clouds may be contributing to. A second contributing process that we're investigating is ice nucleation. Here we want to determine the impact of 4 different ice nucleation schemes, which I've listed here, on the cloud optical depth feedback using NASA's GEOS-5 model. And each of these simulations were run in the AMIP configuration, meaning fixed SSTs and sea ice, and also in the AMIP-4 configuration, where SSTs were increased uniformly by 4 Kelvin. So now changing ice nucleation in the model naturally impacts SLF, or T5050 in these simulations. And the SLF appears to be split into 2 groups. So we have the Barahona and Myers group being on the low end of the SLF spectrum, and then the Ulrich and DeMott being on the higher end. So now when we look at SLF in tandem with the Arctic cloud optical depth feedback values on the right here, we indeed find that the low SLF values correspond to more negative cloud optical depth feedback values, where the high SLF values correspond to less negative values, which are consistent with the cloud phase feedback. However, despite the similarity in SLF between the Barahona and Myers simulations, the cloud optical depth feedback values are quite different. And we see the same for the high SLF pair, the Ulrich and DeMott simulations. So this now takes us into the potential constraints part of my talk, where I'll propose an additional potential constraint for the cloud optical depth feedback. What we're looking into is the possibility that ice crystal number concentration, which is closely linked to ice nucleation, is needed in addition to SLF to explain the difference in Arctic shortwave cloud feedback. And I've illustrated this conceptually using this highly idealized diagram. So your typical definition of SLF only takes mass into consideration. However, when ice number concentration is not accounted for, the optical depth and therefore the reflectivity of the cloud can be very different from what your mass-only definition will tell you. So for example, while both these clouds on the left-hand side have the same SLF when defined using the mass-only definition, you can see that the clouds here with higher ice number concentration are actually more opaque than the ones at the top panel here. So in a global warming scenario, this will impact the cloud phase feedback because the liquid droplets that end up actually replacing the ice crystals in the mean state of the mixed phase clouds are much more reflective than those in the original state, making the cloud optical depth change weaker in the case of the clouds with the higher ice number concentration. So in other words, for the same SLF, clouds with lower ice number concentration will have the more negative cloud optical depth feedback. So this appears to be the case for our GEOS5 simulations. The simulations with approximately the same SLF, but with lower ice number concentration, have more negative shortwave cloud optical depth feedbacks. And this suggests the importance of cloud microphysics, and that ice number concentration might actually be able to provide a tighter constraint on the cloud optical depth feedback. I also wanted to quickly point out or quickly mention that I'm trying to look at this relationship in the CMIP models as well, but there are currently only 3 models available in the archive, and they also don't distinguish between ice in mixed phase clouds and ice in cirrus clouds. So at this point, it would definitely be helpful if the modeling centers could upload that variable to the archive. So finally, just to sum up here, there's a growing number of studies suggesting the possibility of a positive extratropical cloud optical depth feedback that might contribute to a higher climate sensitivity. In terms of physical mechanisms, shifts from stratocumulus to cumulus clouds in a warmer climate might contribute to a positive extratropical cloud optical depth feedback. Ice nucleation is another physical mechanism that impacts the feedback, and simulations with the GEOS5 model so far seem to suggest the possibility that ice number concentration might potentially provide a tighter constraint on the feedback. So thank you for your attention, and I'll be happy to take any questions.
Thanks, Ivy. That was a very interesting talk. Okay, everybody. So if you have a question, either raise your hand in the chat or raise your hand or type it up in the chat. Okay, so we have a question from Nader. Would a stratocumulus to cumulus shift also be detectable as a cloud fraction feedback rather than an optical depth feedback?
Yes, absolutely. So in general, I guess in the subtropics, most people are thinking of the stratocumulus to cumulus shifts as a cloud amount feedback, and it's mostly affecting the cloud amount. But what we've done is using our method, we are looking at the cloud optical depth aspect of it by holding the cloud amount feedback constant. That's the cloud rear kernel method, which I haven't shown in this presentation, but it's something that we are going to look into as the next step.
Okay, thank you. Any other questions for Ivy? Okay, well, if not, we can move on to the next talk. And if you can think of questions, just type them in the chat and we will come back to them for a few minutes at the end in the Q&A session. So, okay, thanks again, Ivy. Our next speaker is David Romps, a professor of atmospheric science at Berkeley. And this is going to be a bit of an experiment. David has sent us a recorded talk, which Andy is going to play.
That's right. So so sharing that. So Christy, can you see that?
Yes, I can see that.
Okay. All right. Here we go. Oh, I'll say David is online. So if you have questions, since he's not talking, you can type questions in and he might be able to answer on the fly.
Yep, I'm right here. I just have terrible internet, so it's better to pre-record these things.
That's right. Yeah. So he is online. Just all right. Here we go.
Hi, I'm David Romps.
Did you hear that?
Yes.
Yeah, that works again.
I have to not mute myself. That's the problem. Okay, so I will let me start over. Sorry about that. And I will keep myself. I'll just be very quiet.
And I'm going to try to make the case that we should spend more effort trying to understand the planet at very high CO2 concentrations and very high temperatures. So the title of my talk, if I can put myself in the corner here, is the ECS bump. If you push the planet out to very high temperatures, there's growing evidence that ECS, the equilibrium climate sensitivity, is not constant, but actually increases and experiences a peak out at high temperatures. So I want to really begin here by thinking about the Eocene. So the Eocene is a time where you've got, guys with great big horns over here, and you've got the birds eating mammals over here, but so lots of weird stuff, to us at least. But what's important for the purposes of this talk is that the Eocene is very hot, as you know. And if we look at the temperatures over the Phanerozoic, with current day over on the right, we go back in time, then the Eocene, some 50 million years ago, is one of the hottest times during the Phanerozoic, with temperatures some maybe 14 Kelvin above pre-industrial. If you want to find temperatures or climates that are warmer than that during the Phanerozoic, you have to leave our home of Earth and go to Venus. And on Venus, things are so hot that, of course, lead melts down at the surface. So Venus has gone through a runaway where it was unable to shed heat by increasing its temperature, so it just ramped up in temperature until finally it could shove radiation out a different window, and it's locked now in this runaway state. Now, common wisdom is that we cannot push Earth to a runaway state by burning fossil fuels, but we should probably make sure that we understand that really quite well, and we should also understand if there are any other surprises waiting for us at very high CO2 or very high temperatures, because it doesn't take a full runaway to kind of ruin your day. And so some of the evidence that's began to accumulate over the past 10 years, it comes from a variety of papers, and I'll touch on just a few of them here. The first is this paper by LeConte et al. In 2013, where they showed that as you increase the solar flux, the response of the planet is not just linear. As you get out to higher solar flux and higher temperatures, the planet starts to warm more for each increment of additional solar flux. So the sensitivity of the planet increases. So that's an indication that something nonlinear is going on at these warm temperatures. A couple of years later, Wolf and Toon had this paper where they looked at 3 different climate models and probed that increase in climate sensitivity. In fact, they probed it so well that they found it was a bump. They went up one side and back down the other, showing that at high temperatures, maybe, starting around 300, 310 Kelvin or so, you start to have this growth, this peak, this bump in equilibrium climate sensitivity. A year later, Max Popp and colleagues tried to probe this in more detail. And what they're showing here are time series. So the x-axis is time, and the y-axis is the global mean temperature. And each different colored curve is a different GCM simulation. One would say a different solar flux or a different CO2 concentration. And what they find is that they can't quite seem to get a GCM to settle down, to equilibrate with a global mean temperature between 300 and 330 Kelvin. So if they try to just inch up the CO2 to just slightly push a GCM up into that gray region, as soon as it gets there, it says, I don't want to be here, and it flies off to above 330 Kelvin. So that means potentially that what we're talking about here is not just an ECS bump, but an infinite ECS. And if it takes only an infinitesimal increase in CO2 to give you a 30K increase in mean temperature, then that's effectively an infinite ECS. Okay, so we're seeing nonlinearity, we're seeing bumps, we're seeing this potentially infinite ECS. That's a lot of weird stuff going on at high temperatures. Now, I want to make the point about some context here. So here I've scaled down that plot and made, so we can see a larger range of temperature. So going up to 800 Kelvin here. So if we look at Venus, a full Venusian runaway is all the way up here at 700 some Kelvin. And what's happening in the simulations down here is really at a much smaller temperature range. So maybe we could call this a terrestrial mini runaway. It's not a full runaway, but it's certainly something weird going on, and by weird I mean also bad, in that it would push the planet to very warm temperatures. We shouldn't take solace in the fact that we wouldn't melt lead. If you actually go up to these temperatures, they would be lethal. And by lethal, I mean that if you try to go outside, you would perish in a matter of minutes. And to those of you who say, well, I go into a sauna, and the sauna's temperature is at least this high, so this can't be that bad, I'll remind you that the relative humidity in a sauna is low, measured in typically single digits of %. Whereas here, we'd have typical terrestrial relative humidities, and it would be absolutely lethal. So this is not a good climate. This is not one we want to ever push towards. So, do we have to worry about this? And the answer is maybe yes. Because if we go back to the Eocene, what was the temperature of the Eocene? It was global mean temperature just above 300 Kelvin, maybe sitting right around here, just inside this gray zone. And so today the continents are in different places, we have different vegetation, but are we so confident that we could push ourselves to an Eocene climate and not fall off the precipice? I think that's a really important question for us to answer. Like I said, we definitely have the fossil fuels to go there, the 5 teratons of fossil fuel plus however many teratons of methane clathrates might get released. We can almost certainly push ourselves back to this kind of Eocene climate. So we should know what the planet might do in response to that human behavior. So if we look at these 3 different studies and just kind of vertically align them on a temperature axis, we see they're all doing funny stuff and around the same place, maybe 300 to 320 Kelvin. And so there's some questions we might want to answer about this. What role do clouds play in this bump? Are they an essential piece, or are they just slight modifiers of what's going on? What does this bump really look like? If you look at the middle one here, there are 2 simulations that are spanning 25 Kelvin. Well, if this bump is really there, we want to know, one, is it infinite? And if it's not, what does it look like? We want to probe it at much finer temperature increments. So to get at those types of questions, I wrote this paper, which I feel like I wrote ages ago, well before the pandemic, but it just came out a couple months ago. And what it does is it explores this ECS bump in a cloud resolving model to see what maybe role clouds play, and to really sample that bump in really high detail. Now, to do that, I have to stray a bit from the standard methodology. The standard methodology is you set the CO2 concentration and you let the SST equilibrate to that. That's a fine way of doing things. The problem is it's very slow. So alternatively, what I've done here is something different. I've fixed the SST and let the CO2 evolve prognostically. So I give the CO2 an equation, prognostic equation, that is going to asymptote to a value that would close the top of atmosphere energy budget. And it's not obvious a priori that that would be faster, but if you work through the math and then actually try it, you see that it is. It's about 30 times faster to get to equilibration than the standard Slab-Ocean technique. Or another way of phrasing that is you buy one and get 29 free. And if you're trying to probe temperature over really fine gradations, then you could really use those 29 free simulations. So that's the technique that I use in this paper. Then you crank up a whole bunch of cloud resolving models, set the SSTs in 1 Kelvin increments, solve for the CO2, let everything equilibrate, and then you can read off what the forcing is as a function of SST and also the climate sensitivity. So when we do that, what we see is that the forcing increases monotonically as a function of global mean temperature, and the climate sensitivity has this bump in it. It's not as big a bump as you get in the GCMs, but it's there, and look, it's in the same place, around 310 Kelvin or so. If you multiply those two together, you get the ECS, the equilibrium climate sensitivity, which has this rising behavior and that bump. Okay, and we also see, because we probed this at really fine temperature gradations, that there's no infinite ECS, at least not in this limited area RCE cloud resolving model kind of setup. If there is an infinite ECS behavior in a GCM, it is likely due to some aspect of the large-scale circulations, interactions with maybe clouds. So something we need to understand. So what we get out of this is we learn that it's a clear sky phenomenon. I didn't show that in the paper, but if you take away the clouds, you get basically, qualitatively the same thing. And we can also show that it's not just an artifact of the radiation scheme, which is something I worried about in the beginning. If you rerun the cloud resolving model with line by line radiation code, you get qualitatively the same thing. Okay, so this gives you a hint that maybe you don't need a cloud resolving model if clouds aren't that important, at least for the kind of single column RCE picture. And in fact, I think that's right. This 2013 paper by Mariner et al. Used a very simple single column model, which was just a model of that had a moist adiabat, and it pegged the column to 80% relative humidity. And what they found was an ECS bump. So this really is just a fundamental aspect of something going on with radiation, maybe water vapor, almost certainly the moist adiabat, the temperature structure of the column. So how does that then relate to what's going on in GCMs? And I don't have the answer to that. But what I can do is collect some of the results that are in the literature. So that's what I've attempted to do here, is to take different simulations from different papers and put them all in a common footing to see if there are consistent behaviors. Because some papers report a bump, some don't, but are they probing the same temperatures? So this is a way to get at that. If we look at forcing, we see that forcing increases monotonically in all the simulations that I have data on here. So that's nice to see consistency there. If we look at -1 over the feedback parameter, or what some people call the climate sensitivity, we see a bump. We see a spike there. My cloud resolving simulation is the brown dot dash curve at the bottom. This bump is much less than what you see in the GCMs. Again, something we need to understand. Why is there that difference? If you multiply this together, you get the ECS. And only 4 of the simulations have probed the ECS bump, to the best of my knowledge. And one of them is my cloud resolving model. The other is that very simple RCE model, the moist adiabat model. And then 2 are GCMs with the higher ECS bumps. This is something I think we really need to understand better. And but to do that, I think we should be running GCMs, and we should be probing at very fine temperature intervals. And so a proposal that I have at the very end of this paper is the very last paragraph. If you want, you can skip the whole paper, go to the last paragraph, and it's a proposal for how to speed up these equilibrations in a global climate model. I'm not sure it works. I haven't tried it, but I think it's promising. And it might be a way for us to get at this problem and really understand what this ECS bump looks like in a variety of different models. Again, we have the ability, unfortunately, to push our climate back to an Eocene-like state. And so we should understand what waits for us there in that Eocene-like state. Is there a cliff that we can fall off or not? So I'll end there. Thanks.
Okay, well, thanks. Let's see. I'll just make a comment that I guess Linzen was correct. Climate sensitivity is low, but what he didn't tell you is you have to get the climate to 350 Kelvin for that to be true. All right, so do you want to, let's see, so Christy, do you want to run the questions?
Yeah, sure. Looks like we have one from William Collins. You should be able to unmute yourself now.
Thank you. Thank you, David, for a great talk. If this is due to clear sky radiation, then I don't know if you looked at this in the line-by-line models, but there are several plausible causes for this. One would be that you're filling in the mid-infrared window in water vapor. So that would certainly cause the planet to become more opaque in the infrared. A second might be that there are overtone bands from CO2 that you're dropping into the mid-infrared window, thereby blocking it. And the third thing that could happen, and I've thought about this, is when you make the planet appreciably hotter, you move the you start to move the Planck function out of the mid-infrared window and into the water vapor bands between 5 and 7 micrometers, which again sort of reduces your ability to cool, because now you're starting to see more and more of the Planck curve in parts of the spectrum where it's opaque. Are any of those along the right lines, or have you looked at this?
Bill, good questions. I don't know the answer to this. We can look at this in a line-by-line code to see what's going on in more detail, and I think there are people on this call who have maybe already done that, but I won't speak for them. But I would be surprised if the shift of the Planck function is what's responsible, because it's such a large effect, and you start to see this by increasing temperature by maybe 20 Kelvin or so. So it's a pretty modest shift, but not impossible.
Okay, thanks. Daniel Cole has a question. David, some of the studies you're referring to were varying the solar constant. Others, e.g. your own, were varying CO2 at fixed insolation. Does forcing matter?
Yeah, so one of the things that, what we have the power to do, of course, is to change the CO2 concentration. So how you map from CO2 concentration to the forcing is important. And so understanding that increase in forcing with temperature is something that's good to understand. And I'm a co-author on a paper that gets at some of that. It's in review. And yeah, I think a lot of this could be done also by increasing solar forcing. It appears to be that this behavior is mainly a function of surface temperature and not of the type or nature of the forcing that's being applied.
Okay, thank you. Question from Lucas Kluft. How did you validate the radiation scheme? We found that the RRTMG lookup tables are out of bounds for surface temperatures exceeding 308 Kelvin, which caused a decrease of ECS estimates. The bump disappeared when using line-by-line radiation.
Right, so I checked the output from RRTMG against a line-by-line code, and found that basically you get the same thing. So I've also taken so what I've done there is I just take mean profiles from the RC simulations and feed those mean profiles into either RTMG or into a line-by-line code. Alternatively, I've actually run the cloud dissolving model with the line-by-line code as its radiation scheme, and you get qualitatively the same behavior.
Okay, awesome. I guess I got one more question for David, I assume, from another.
Yeah, actually, this is just a comment. So Celia and I just submitted a paper doing a spectral dissolved analysis, trying to figure out what causes this this bump. And I guess the short story and clear is that it's the CO2. So as Bill pointed out, the water vapor window closes, and that's what causes ECS to ramp up. At least our clear sky single column 1D RC model. What causes the ECS to go back down is that when you're forcing with CO2, the 15 micron band of CO2, the emission levels up in the atmosphere, and they also occupy a wider frequency band and are able to actually to radiate to space more and more effectively, especially as the moist adiabatic amplification of the upper troposphere causes strong increase in upper stratospheric temperatures, from which that deepens to emissions they're able to radiate from. So that's just sort of a brief story. Again, as David points out, that's just a clear sky piece and a single column making the connection to G-schemes. There's much more work to do. But there's a preprint that should be available soon, and maybe we could even give it in this seminar series.
Cool, awesome. Thanks for that comment. Okay, well, I think because we want to be mindful of the time, we should thank all the speakers. Those are very interesting talks. At least I feel like I learned a lot. And as long as the speakers are willing to hang around for a couple of minutes, perhaps we can keep talking. If not, thanks everybody, and see you at the next seminar. Ivy, Chris, David, do you want to hang out for a couple more minutes?
Yes, I'm still here. Yeah.
Yep, I can hang out for a couple minutes.
Okay, so let's go back and look at some of the earlier questions.
Also, if anyone wants to raise their hand, we can unmute them.
Yep. So let's see. There were some questions for Chris. I think you've already answered Michael's question from Johannes. Hi, Chris. Nice work. Does the sharp peak in ensemble member weights for the ocean heat uptake constraint indicate a systematic problem? And if so, any idea what the problem is?
Yes, I did actually sort of try and answer that one already. That's in the chat already. It's because it's a normalization of the constraint. So basically, the area under that curve would be equal to 1, because we use a root mean square constraint for the temperature. So that can only ever get so close to the observations. I think the best RMSE is probably about 0.1. Whereas for the ocean heat uptake, some of the model runs actually get very close to the observations because we use a linear trend. So they kind of bunch up together. But actually, we did try a root mean squared for the ocean heat uptake as well, and the results are very similar. We just decided it would be more appropriate to use a trend for that constraint.
Okay, thanks. So a question from Klein21. I assume this is Steve, maybe? Did I understand correctly that you are assuming that the feedbacks lambda derived from the historical warming are the same as those applicable to long-term warming? Do you think this is an appropriate assumption? There has been a lot of separate work questioning that assumption.
Yeah, yes, I understand that concern. So we derived our lambda from 4 times CO2. So it's not really sort of trying to estimate ECS from historical observations as such. What we could do is apply a pattern effect to our historical runs, which would probably have the effect of lowering the sensitivity and lowering the aerosol forcing. Although if we did that, then we wouldn't be. There's kind of 2 problems really. The first thing is we're not measuring ECS anymore because we have that sort of pattern effect, and we have a different lambda for our sort of historical period as we would do for the future. And the second thing is where do we get it from? How do you transition from the kind of present pattern effect or the historical pattern effect into the future? So I know, so we've only looked at the historical up until now, but in general, if we want to transition to try and make projections using this method, we need to assume a way to transition from that current pattern of SSTs to the 4 times CO2. So you have to then consider timescales, or possibly this present pattern is actually indicative of a long-term trend, which has not been reproduced by the model. So there's lots of different complications introduced by doing that.
Cool, lots of interesting stuff to work on there. Okay, there's a question by Gita. Have you assessed the relative contribution of SO2, OC, and BC, just black carbon, changes to the time evolution of forcing in each model? Any chance differences in mixing or optical properties across models and the effect that has on the relative importance of each aerosol type could explain when that peak occurs?
Yeah, that's a very good question, actually. So we didn't. It was a curve fitting method. So it is a statistical way of fitting aerosol precursor emissions to a forcing. It has got some physical basis. So for example, that linear relationship for the direct aerosol forcing, those coefficients in each model they're as expected. They're positive for BC, they're negative for SO2, and the mean of those coefficients are in line with studies that have looked at this sort of single forcing experiments in sort of ACMIP, I think it was, sort of study that informed CMIP5. So even though they're statistically derived, the coefficients for the direct forcing are actually sort of quite realistic. But that's about as far as it goes in terms of the actual sort of aerosol physics. So there's obviously a lot of improvements that could be made to this method. So firstly, we've assumed a global total emissions corresponds to a particular unit of forcing. Now, obviously, aerosols are sort of very regionally diverse and have lots of different sort of regional effects. But the kind of by varying that, by using a probabilistic ensemble, we hope to take some of that variability and uncertainty into account just by the way we sample it. So it's a very good question, and I think there's lots I'd like to probe with the aerosol emissions, and lots of good science to do there.
Cool, thank you. I think, as far as I could tell, all of the other questions have basically been answered. Oh, there's a new question for Ivy from Yoko Tsushima. Hi, Ivy. In the phase feedback, changes in precipitation efficiency is another contributor to negative feedback. Are you planning to look at the efficiency in an ice cloud and liquid clouds and the influence of ice on liquid?
Yes. Hi, Yoko. Yes. So, right. Precipitation efficiency is an important factor influencing the lifetime of the clouds. So, typically the ice clouds will precipitate out faster than the liquid clouds. And so that can impact the phase partitioning, the opacity of the cloud, and its lifetime. So far, I haven't looked into that yet. It's really difficult to get observations of that, as I'm sure you know. So far, I haven't done anything on that, but that is definitely an interesting question that has yet to be looked at.
Cool. Well, I think that's it, except for Mark's question as to whether David can lip sync to his own video. But I think we can defer that.
That would have been a challenge.
Okay, well, thanks everyone. And I don't know if Andy has anything else to add. If not, we'll see you next time.
No, thanks a lot. And if anybody wants to volunteer to give a talk, email me and Christy. We're always looking for volunteers. So thanks, guys. That was really good.
Thank you, Andy. Thank you, Christy.
Thanks for organizing this.
Yeah.
Yes, and thanks for the good questions. Bye, everybody.
Thank you.
Bye.
Bye.